So here we're going to learn about a new thermodynamic concept that probably be the first time many of you have ever heard of it, known as entropy. Now, we've talked about enthalpy of reaction. That's a delta H reaction. That's heat of reaction at constant pressure. Entropy is a different kind of concept, but is tied to delta H, has a relationship with delta H. So before we discuss and define what entropy is, let's take a very simple system. And I have a box. And I have a box that has 4 holes in it, and I have 4 red circles. And there's only one way that I can sort of arrange those 4 circles into my 4 boxes. So the number of combinations, if you will, unique combinations, is only 1. But if I take that same box, or the same set of 4 boxes, but I have 1 triangle and 3 red circles, then I actually have 4 different combinations. Basically 4 different ways I could sort of arrange everything. So the triangle could be in the upper left-hand one, it could be the upper right-hand one, it could be here, or it could be here. And if I have 4 boxes, but I have 2 triangles and 2 red circles, then I actually have 6 combinations, because if I think about the red triangles, could be in this position, or I could have the red triangle here and here, or I could have the yellow triangles there and there, or there and there, or above and below, above and below. So as we sort of like change up the number of things, so in this case we only had 1 thing taking up all the positions, so there's only 1 combination. As we sort of like change the variety, if you will, I can increase the number of combinations. And I can also, if I increase my number of positions, I can also increase it to a point. So in this case, I have only 1 combination, even though I have many more spots. Now I have 10 spots, but there's only 1 way to arrange 10 red circles. But if I have 9 red circles and 1 triangle, well, now I've gone from 1 combination, now I go immediately up to 10 combinations, because I have more positions. And then of course, if I have 2 triangles and 8 red circles, my combinations goes up even more. So the definition, if you will, of entropy is exactly this. This is the strict definition of entropy. It's related to, or directly proportional to, the number of microstates. And the microstates is all these combinations. So in this case, the number of microstates here is 4, the number of microstates here is 6. It's how many different combinations you can put it in. And of course, we don't think about it that way in the real world, because on the atomic level, it's just a ridiculous number. But this is the definition of what entropy is. And entropy is a state function, so it's just like delta H, that it doesn't matter sort of like your path that you got there. All that matters is the present state of the system. And it's also an extensive property, meaning the entropy changes depending on how much you have. So entropy is another way of thinking about entropy, or the common way of thinking about entropy, is in terms of disorder. The more disordered, more combinations you have. If you have a very ordered system, it doesn't have very much entropy. As you increase the disorder, if you will, the entropy increases. So there's a couple of different ways of increasing the entropy of the system. So simple phase changes. So if I take a solid, which remember has all of our atoms in a very rigid structure, and we melt it, turn it into a liquid, the entropy will of course increase, because now the molecules are free to sort of like move around each other. If I go from a liquid phase to a gas phase, that would also increase my entropy, because in the liquid phase the molecules are still stuck to each other, but in the gas phase they're free to run around independently. If we mix our solids and liquids, if it's a non-electrolyte, we get an increase in entropy, so like the triangles in our previous example. If we increase the total number of moles of gas in a system, that will also increase our entropy, because it's very similar to, you can think of it in a similar way as to adding more triangles to that previous explanation in the previous line. And then of course, if we increase the temperature, then the molecules are moving around faster, and they have more essentially possible combinations with which they could survive in. Now, entropy is defined as the heat of reaction of the reversible, so Q, remember, is heat of reaction, for the reversible reaction. So remember, that was that delta H, or the reversible reactions are the ones where it's sort of at equilibrium, such that if you change the system and then you remove that change, it goes back to its previous spot. So heat of reaction for the reversible reaction. And the units for delta S are joules per Kelvin, right? So joules per Kelvin. And you're also going to see it as joules per mole Kelvin because, again, it is also, because it's usually, we usually talk about the per mole basis because it's an extensive property. So the 0th law of thermodynamics was hot things dump energy to cold things. The first law of thermodynamics says that total energy in the universe is constant. The other two laws of thermodynamics we're going to talk about, we have to sort of now introduce them. And the reason why you've probably never heard of the second or third law of thermodynamics is because to understand them, you need to understand entropy. And entropy is not something that's usually covered in high school chemistry. So don't feel bad if this is the first time you've ever learned about entropy. So the third law of thermodynamics is basically just sort of how we define what S is, right? So the third law of thermodynamics says that a perfect crystal at 0 Kelvin has an absolute entropy of 0, which means it has essentially 1 microstate. So we define that as entropy 0. And entropy is like any other, it's an extensive property, so we need to know how much we have. So the second law of thermodynamics, which is the one that's going to be really important to us here for a while, basically says for a reaction to be spontaneous, the total entropy of the universe needs to increase. That's basically what it says. All spontaneous reactions. So remember, a spontaneous reaction is a reaction that Mother Nature says, hey, yes, I'm going to do that, and I don't need anybody's help. So the rusting of iron is a spontaneous process. The melting of ice at 25 degrees Celsius is a spontaneous process. Any process that is spontaneous, the total entropy in the universe is increasing. That's basically, hey, Mother Nature likes an increase in the entropy of the universe. Mother Nature likes disorder. So the entropy of the universe is the change in entropy of our system plus the change in entropy of our surroundings. Because remember, we have our reaction going on, but there's also, as our reaction is going on, there's an energy exchange, and there's an entropy exchange between the system and the surroundings. So the third law of thermodynamics just says total entropy of the universe increases, it happens by itself. If that's a spontaneous process, and for a non-spontaneous process, the delta S of the universe is less than 0. So in that rare case when the delta S of the universe is 0, then it's a reversible reaction. So if delta S of the universe is non-zero, then Mother Nature sort of like pays attention to it. If the delta S of the universe is 0, this is an equilibrium system, Mother Nature really doesn't care, right? So when I have a system that's at equilibrium and I go in and disturb it, it shifts a little bit. I remove that disturbance, it shifts back to exactly where it was. That's the general properties of equilibriums. And when that happens, Mother Nature doesn't care. So she doesn't care one way or the other, not good, not bad, whatever. So just to sort of for comparison's sake, I just wanted to show you some standard molar enthalpies. So this is joules per mole Kelvin. So here we have hydrogen gas, which is a very simple, small molecule, has a relatively good-sized entropy, and nitrogen is small. And as you see, as we get more and more complex, we get larger and larger molecules, our entropy increases. So benzene has a much greater molar entropy than hydrogen, but benzene has 12 atoms, and they've all got bond lengths, and they can vibrate a little bit. So there's a little bit more positions that they can take on. And then you notice I kind of color-coded to make it easier to sort of see. So water here in blue. So you can see that for water gas, it's 188, and for water liquid, it's at 69.9. So almost 1/3 the entropy when you go down, when you go from the gas to the liquid of associated one. And in benzene goes down by almost 80. And then I put some solids over here to sort of show you that our entropies with solids, because they don't have very many combinations because they're kind of stuck in that matrix in that shape, are relatively low in comparison to our gases. And notice, though, that the standard molar enthalpy of iron 3 chloride, which is in fact a solid, is 142. So this solid has an entropy greater than hydrogen gas, but that's because iron 3 chloride is actually a pretty big species, which explains why. So it's not. My point here is to say it's just like, oh, not all gases are greater than all liquids are greater than all solids. You can have solids that have high entropies, and you can have gases that have low entropies. But in general, I mean, if you compare, the solid and the liquid of the same species, the solid will always have the lower entropy. And just sort of like tie a bow on this, let's consider if I take a chunk of solid that is below the boiling point, and I sort of like graph temperature versus entropy of it. So when I first heat up the solid is changing temperature, and we're just sort of like heating of the solid, and so the temperature is slowly heating, and as we increase the temperature, our entropy goes up. And then when we reach the boiling point, our temperature won't change, but then we'll go through a phase change. So then we'll be going straight up because the liquid level, the solid is melting turning into the liquid. Then once here we are, all the solid is turned into liquid, and now we can heat the liquid again. So this is just the heating of the liquid until we reach a point which we would call the boiling point. At the boiling point, we have the phase change. Everything turns from a liquid to a gas. So our entropy then increases. Notice the relative magnitudes of the height of these graphs. Melting and then boiling is going to be a higher one because the incremental change from solid to liquid is greater than the increase from liquid to gas. And then once all the gas has been formed, all the liquid is turned into gas, then when we heat it, again, the entropy goes up as the temperature goes up.